So now I think it's time to get into all of the physical parameters that make up the equation for the definition of voltage, right? The voltage equation. So the voltage equation is made up of the physical parameters, voltage, work, and charge. Synonyms for voltage, as we said earlier, potential drop, potential difference, electric potential, voltage drop. Synonyms for work would be electrical energy or electric potential energy, or electric energy or electrical potential energy. Electric or electrical doesn't matter. But what is very important here is that if you see the words electric potential, that refers to voltage. If they put electric potential energy, that refers to work. All right? Electrical energy, again, refers to work. All right, so charge. The symbols. The symbol for voltage is V. The symbol for work is W. All right, the symbol for charge is Q, a lowercase q. The unit for voltage, all right, is the joule per coulomb. Joule per coulomb, right, that is known as a volt. And the symbol for that unit is also a capital V. So the symbol voltage and the unit volt have the same symbol. That's fairly unusual in physics. Now, the unit for work is the joule. Okay? That is a joule. Capital J. And the unit for charge is the coulomb. Right? C-O-U-L-O-M-B. Right? The coulomb is the unit. Okay, so now let's take a look at the voltage equation. All right, and let's look at it in terms of symbols, and let's look at it in terms of words. All right, the voltage equation. Here we go. Okay. All right, so the voltage equation, all right, goes like this. All right, symbols, okay. All right, voltage is equal to, all right, the work per unit charge, okay? So voltage, all right, is equal to work divided by charge. And again, keep in mind a synonym for work would be electrical energy or electric potential energy, okay? Now, we should also derive the unit. I forgot the unit. Okay, let's derive the unit for voltage. All right, the unit for voltage is going to be the unit for work divided by the unit for charge. So it's going to be joule per coulomb. All right, that's the unit for voltage. And the special name for a joule per coulomb, all right, is a volt. All right, and that's also a capital V. A joule per coulomb is also known as a volt. All right, now, let's take this equation, let's solve it for W, and let's solve it for Q. We're going to do a little bit of algebra, all right, and solve for the various physical parameters. All right, solved for V. V is going to be W divided by Q. All right, solved for W. All right, it's very easy to cross multiply. W times 1, right, put the V over 1. W times 1 is W equals Q times V, all right, Q times V. All right, so that's solved for W. And finally, solved for charge, all right, Q. Let's divide both sides by V, right? Divide by V, divide by V, all right? And we find that, okay, that Q is going to be equal to W divided by V. All right, now what you could have done to go straight from here to here, V and Q are inversely related, so you can just switch inverses, right? Put the Q up there, the V down there. Put the Q up there, the V down there. And this is correct. Okay, so this is the voltage equation solved for V, solved for W, solved for Q. Please be very careful to solve correctly when you try to use these different versions of the same equation. Follow correct rules for algebraic manipulation. Now, if we're going to convert, right, volts to millivolts or microvolts or vice versa, okay, we're going to have to know how many millivolts there are in a volt and how many microvolts there are in a volt, etc. So what if we start with milli, right, and we look at the fact that 1 meter is equal to 1,000 millimeters. This prefix being milli, and this symbol here being meter. All right? So 1 meter is equal to 1,000 millimeters. So what that means, all right, similarly, is that, right, 1 volt is equal to 1,000 millivolts. All right? That's good so far. All right, now, what about micro? All right, actually, no, let's look at this in a little more depth for just a minute. All right, so this would be 10 to the third meters, all right, or 10 to the third millimeters, or 10 to the third millivolts. Okay, so 1,000 millimeters or 1,000 millivolts. All right, now, what if instead, all right, I'm going to take this away for just a minute, we divide both sides by 1,000, all right, to show that 1,000th of a meter, right, 1,000th of a meter is equal to 1 millimeter. All right, that would also be, see, if you take an equality that's true, 1 meter equals 1,000 millimeters, and manipulate it algebraically in a correct fashion, for example, dividing both sides by the same number, you're going to get another equality, all right, equality written in the same equality written in a slightly different way that is also correct. So 1,000th of a meter is 1 millimeter. I think you know all this. All right, so that also means that 1,000th of a volt is 1 millivolt. Okay, so you want to write down, all right, that 1 volt is 1,000 millivolts, and 1,000th of a volt is 1 millivolt. Okay, those are both correct. You can use one or the other for converting between volts and millivolts. Now, what is this micro? All right, well, micro means 1 millionth. The same way that milli means 1,000th, micro means 1 millionth. All right, so 1 volt would be 1 million microvolts. All right, this is the Greek letter mu. All right, it's kind of like a U with a tail in the front. Here's the U, here's the tail in front. I tend to make the tail and then make the U. I guess I'm exaggerating the tail a little too much, but that's okay. All right, so 1 volt equals 1 million microvolts. All right, now if we divide both sides by 1 million, all right, then 1 millionth, now 1 millionth would be 10 to the, I'd rather not write the 0.000, etc. All right, 1 millionth, all right, 10 to the negative 6, or 1 times 10 to the negative 6 of a volt. A millionth of a volt is 1, all right, microvolt. Okay? So micro means 10 to the minus 6th, or 1/millionth. Okay, so now let's do some conversions, all right, from volts to millivolts, or millivolts to volts and microvolts, okay? Let's try first 7,500 millivolts. All right, 7,500 millivolts, all right, and we will convert that to volts. Okay, we need to know, right here, millivolts we want to get rid of, right? We want those to go away, and we want volts. Okay, so we need to put in here that these need to equal each other. The numerator must equal the denominator. All right, so you could put 1 volt equals 1,000 millivolts. Okay, so we take the 7,500, divide it by 1,000. So really you could just take this and move it 1, 2, 3 places, and we're going to get 7.5 volts. All right, or you can pick up your calculator, 7,500, look, divided by 1,000. The 1,000 is on the bottom, so divide. You're not cross-multiplying. The equal sign is over here. Okay, I want to emphasize that. A lot of people try to cross-multiply this. You can't. The equal sign is over here. So don't cross-multiply with a factor label method. All right? So 7,500 millivolts equals 7.5 volts. How about 8 volts? Let's convert that to millivolts. All right, 8 volts. We want to convert that to millivolts. All right, we want to get rid of volts. Volts on top, volts on bottom are going to cancel. Millivolts. All right. Let's try something a little different. All right, 1 times 10 to the negative 3 volts is 1 millivolt. Okay, so let's pick up the calculator. All right, and let's do 8 divided by this. Okay, 8 divided by 1 times 10 to the negative 3. All right, we're getting 8,000 millivolts. The volts cancel, we get millivolts. All right, we got that. How about micro? All right, let's try some microvolts. All right, let's try 0.0025 volts. Let's convert that to microvolts. Okay, volts. All right, I want to get rid of volts. I want microvolts. Okay, 1 volt equals 1 million microvolts. All right, take 0.0025, multiply by 1 million. You're really moving this, right, 6 places to the right. All right, but here we go. 0.0025 times 1,000,000. All right, 2,500. 1, 2, 3, 4, 5, 6. Yes. All right, 2,500 microvolts. Okay. Try one more. All right, let's say we have 50,000. All right, microvolts. I want to change that to volts. I want to get rid of microvolts. Top, bottom, they're going to cancel, right? I want volts. Okay. 1 microvolt is 1 times 10 to the negative 6 volts. All right. I could have put 1 million down here, right? And 1 up here. I could have put 1 volt equals 1 million microvolts. I could have done that, right? You can use this equality or this equality. Because remember, again, okay, I'm just going to put it over here for just a second. Right, 1 volt is equal to 1 million microvolts. And 1 microvolt is equal to 1 times 10 to the negative 6 volts. All right, so you can take this equality, you can put it here or here. It doesn't matter. You just got to put the right one on top and the right one on bottom. All right, that's why I always say, okay, if I have volts, I want to get rid of volts. I put the units in first in the correct places. Then I put the correct numbers with the correct units based upon my equality. All right, so either one of these you can use in here, as long as you put the numbers in the right places. Okay, so here we go. 50,000 times this here, 1 times 10 to the negative 6. 50,000 times 1 times 10 to the negative 6. All right, 0.05 volts. Okay, so there we're converting volts to millivolts, millivolts to volts, volts to microvolts, microvolts to volts, etc. Okay, you need to always convert to volts. All right, if you're using joules and voltage, you need to always convert to volts. All right, don't use microvolts or millivolts. Always convert to volts. The same way that you always convert to seconds or coulombs, right? When you're calculating the current, right? And here also you're going to have to convert. If you get microcoulombs or millicoulombs, convert to coulombs. So use again, all right, volts, joules, and coulombs. Right? Volts for voltage, joules for work, and coulombs for charge. All right, don't use microvolts, don't use microcoulombs, all right, etc., etc., etc. Okay, just for now, just for this section. Okay, maybe we'll expand on some of these ideas in later sections. Okay, thank you. All right, here's our first problem using the voltage equation. It says calculate the voltage drop. We know that's a phrase that means voltage. Now the word across is going to come up a lot when you're talking about voltage, because we talk of voltage, we speak of voltage as being as traveling across or through a component or a device, such as a resistor. All right, so you're going to see that word across very often when they're referring to voltage. Calculate the voltage drop across a resistor if it dissipates means it uses up, right, 200 joules, that's a decimal point, all right, 200 joules of electrical potential energy. Remember, electric potential is voltage, but electric potential energy is work, or W. All right, so voltage drop is V, all right, electrical potential energy is W for every 5,000 microcoulombs of charge, and charge would be Q. All right, so let's see what we've been given, all right, and what we are trying to find. And then we will select the correct formula. Calculate the voltage drop, right? We're being asked to find the voltage. Okay, that's in volts, and that's the question mark. Across a resistor, if it dissipates 200 joules of electrical potential energy, so W is 200 joules. For every 5,000 microcoulombs, the charge is 5,000 millicoulombs. Ooh, millicoulombs, not micro. Millicoulombs. Okay, be careful. Micro is that, all right, not M. All right, that's millicoulombs. All right, so 1,000. All right, 1,000 of these to a coulomb. All right, formula. Okay, formula. So let's pick a formula. We're trying to find V. We have W and Q. So what comes to mind right away is the classic definition equation for voltage. V equals W over Q. All right, so we have to convert millicoulombs to coulombs before we get started. So let's do that quickly first. All right, we'll change the millicoulombs to coulombs, and then we'll get started. So 5,000 millicoulombs. All right, now I want to get rid of millicoulombs. See how that's over 1? Millicoulombs on top, millicoulombs on the bottom. The millicoulombs are going to cancel. Coulombs. All right, so I need numbers in here that equal each other. One big giant coulomb is 1,000 little millicoulombs. 5,000 divided by 1,000 is 5 coulombs. So this 5,000 millicoulombs becomes 5 coulombs. Okay, and here we go. The formula, V equals W over Q. All right, so W is 200 joules divided by 5 coulombs. All right, pick up your calculator. 200 divided by 5, all right, is 40 volts. All right, the voltage is 40. We've got how many significant figures? Well, if we put a dot there, we'd have 3 significant figures. 40, all right, joules per coulomb, or you could say V is 40 volts. Okay, nice and simple. Let's do a problem where we're solving for, what are we solving for next? Work, electrical energy, next. Okay, in this problem, we're being asked to calculate the amount of electrical energy, so that would be W, possessed by 2 times 10 to the 7th microcoulombs, that's your charge. Now microcoulombs we're going to convert to coulombs, all right? Microcoulombs of charge, right? If they have just exited a 4,000 millivolt, all right, that's our voltage battery. Okay, so we've got W, Q, and V. All right, we know what equation we're going to use for that. All right, so what have we been given? What are we trying to find? All right, and we know what equation we're going to use, but let's use the space here to convert the microcoulombs and the millivolts, and then we'll put our equation over here. All right, calculate the amount of electrical energy. We're being asked to find W. That's in joules. That's the question that we're being asked. 2 times 10 to the 7th microcoulombs of charge. The charge Q is 2 times 10 to the 7th microcoulombs. All right, if they have just exited a 4,000 millivolt battery. All right, volts is 4,000 millivolts. Okay, let's convert the microcoulombs to coulombs. Okay, so 2 times 10 to the 7th microcoulombs. All right, we want to get rid of microcoulombs. We want coulombs. One coulomb is 1 million microcoulombs. All right, so we take the 2 times 10 to the 7th, divide it by 1 million. All right, 2 times 10 to the 7th, divided by 1 million. And we get 20 coulombs. All right, 20 coulombs. All right, so let's erase this and put 20 coulombs instead. All right, 20 coulombs. Now the millivolts, we want that to be in volts. Okay, now look, I'm doing a lot of converting. In most problems that you're going to come across, you're not going to have to do this much converting. In most problems, they're going to give you coulombs, they're going to give you volts, they're going to give you joules, right? But if you see microcoulombs, if you convert to coulombs, if you see if you see minutes, convert to seconds. If you see millivolts, convert to volts, all right? 4,000 millivolts, all right? I want to get rid of millivolts. See how I put the units in first in the right places? So there's no screwing up what goes on top, what goes on the bottom. Where do I put the 1? Where do I put the 1,000? All right, it's one big giant volt is equal to 1,000 little bitty millivolts. 4,000 divided by 1,000, we know is going to be 4 volts. All right, so right here, the 4,000 millivolts becomes 4 volts. Okay, so now here we go with the equation. All right, the correct equation. We're trying to find W. We've been given Q and V. So how about, all right, for the formula, all right, how about V equals W over Q? Okay, so, nope. How about W equals? All right, W equals Q times V. Better version, okay, for this. We're trying to find W. All right, Q is 20 coulombs. All right, V is 4 volts, but a volt is a joule per coulomb, right? So the coulombs cancel, and we get the joules that we're looking for. Joules are the correct unit for work, so everything's working out. 20 times 4, all right, 80 joules is the answer to this question. Okay, calculate the amount of charge that has passed through a resistor if the electric potential, now remember, electric potential is voltage, right? Electric potential. Charge, all right, is Q. Electric potential is V for voltage. If the electric potential across, there's that word across again, referring to voltage, all right, or electric potential. If the electric potential across the resistor was 10,000 millivolts, and the electric potential energy, all right, see how electric potential is voltage, but electric potential energy is W, okay? Dissipated was 20 joules, okay? Now, let's right away change those millivolts to volts, okay? Because we have very little space down here. 10,000 millivolts, okay? Millivolts to volts. All right, 1 volt is 1,000 millivolts. 10,000 divided by 1,000 is 10 volts. Okay, so this is 10 volts. All right, 10 volts. Okay, so I'm going to get rid of the W also. All right, given. What have we been given? What are we trying to find? Calculate the amount of charge. So we're trying to find Q. Q is coulombs. There's the question mark. That has passed through a resistor. If the electric potential, the voltage, was 10 volts, and the electric potential energy, the W, right, was 20 joules. Okay, we're trying to find Q. Now, formula. We know that V is W over Q. But what if we're trying to find Q? How do we get Q by itself? Well, V and Q are inversely related, so you can switch the inverses. Right? Put the Q up here, the V down there. Okay? So, put the Q up here and the V down there, and we still have a correct equation. And I think I'm going to go this way because I'm running out of room here. All right, 20 joules, all right, 20 joules divided by 10 volts, all right, 10 volts. All right, now actually a volt, right, is a joule per coulomb, okay? So we're going to get 20 divided by 10 is 2. All right, now, how do I resolve these units here? This one gets inverted, all right? Coulombs per joule, coulombs per joule. All right, those cancel, everything on the bottom is canceled. This is joules on top, joules on the bottom. The joules cancel, I get coulombs, which is correct because I'm looking for charge. So there's your coulombs. All right, so the answer here is 2 coulombs. Okay? All right, once again, as in the last section, I'd just like to do 2 problems where we're converting electrons to charge, and then in the very last problem, charge to number of electrons. All right, so let's see what this question here is asking. Calculate the amount of electrical energy. All right, they're asking us to find the W, all right, the work. All right, so given, all right, find. We're being asked to find W. All right, W equals a certain number of joules. All right, if the electrical energy used by a resistor, if 1.875 times 10 to the 19th electrons, so they're giving us n, the number of electrons is 1.875 times 10 to the 19th electrons. It seems to me we're going to have to convert that to Q charge. All right, we'll do that in just a minute. Pass through with a voltage of 20 volts. So the voltage is 20 volts. All right, now it seems to me that if we were to use the equation, right, V equals W over Q, rearrange it for W, right, I'm going to cross multiply. W times 1 equals Q times V. Right, so if we were to use this version of the equation, we could figure out the work done, or the electrical energy used by the resistor. But we're going to need charge, not number of electrons. So let's convert this many electrons to charge Q. Right, there's two ways we could do that. Okay? As a matter of fact, I think I'm going to erase, all right, why don't you copy down the question if necessary, because I think I'm going to erase that. I need more room here. Okay? All right, here we go. All right, so there's two ways we can convert these electrons to coulombs. It really doesn't matter which way we use, but I would like to show you both ways. All right, 1.875 times 10 to the 19th electrons, okay? I can say, all right, electrons to coulombs. All right, I can say that in 1 coulomb, there are this many electrons, 6.25 times 10 to the 18th electrons. So that means I'm going to take this number and divide it by that, divided by, right, that number. Okay, so 1.875 times 10 to the 19th divided by 6.25 times 10 to the 18th. All right, gives me 3 coulombs. Okay, I actually have 3 significant figures there, right? Because I got 3 of them here, so we'll say 3 coulombs. All right, so I've got 3 coulombs instead of this many electrons. I'm going to switch that right now, and just show you one other way that you might remember to convert electrons to coulombs. So the charge is 3 coulombs. Now, what's another way that we could do that? What we could do instead, all right, is take that number of electrons and say that 1 electron, right, has a charge of 1.6 times 10 to the negative 19 coulombs. That is also true. So if I take this and multiply by that number, 1.875 shift E 19, right, times 1.6 times 10 to the negative 19, all right, we're still getting 3 coulombs. Okay, except this time we only have 2 significant figures. All right. Okay. So, back to the rest of the question. All right, I've converted electrons to coulombs, and now I'm ready to use the equation that defines voltage. All right, voltage. What formula are we going to use? Voltage is equal to work divided by charge. I'm going to cross multiply and get W by itself because we're trying to find W. All right, so W equals Q times V. Okay, the charge is 3 coulombs. The voltage, 20 volts. Now remember that a volt is a joule per coulomb. All right, so the coulombs cancel, all right, and we're getting 60 joules for the answer. And we should be getting joules because we're trying to find the work or electrical energy. Okay, remember, it's very easy to convert from coulombs to number of electrons to coulombs, because we know the charge in coulombs on 1 electron And we know also how many electrons there are in 1 coulomb. Okay, I would like to convert, getting a little crazy here with the, I would like to admit, I'm getting a little crazy here with the converting. All right, you're going to see here we've got millijoules. In most problems, it's just going to say joules. You don't have to convert anything. And microvolts, most problems are just going to say volts. You're not going to have to convert anything, right? But I do want you to get comfortable with converting. So I'm throwing you into the fire. And hopefully a lot of the questions you do will be a little bit easier than this. All right, here we go. How many electrons? All right, now, you know if they're talking about joules, all right, of electrical energy, you know that's W, right? Let's start listing what we've been given and what we're trying to find, all right? How many electrons? All right, we're trying to find N, all right, the number of electrons, okay, must pass through a resistor to dissipate 500 millijoules of electrical energy. So that's W, all right? Your energy or work, electrical energy, is 500 millijoules. We know we're going to have to convert that to joules. If the voltage drop, right, that's voltage, is 20,000 microvolts. So we've got volts, 20,000 microvolts. Okay, now, we recognize right away that we can use the formula, all right, because we've got W and V, and we're trying to find the number of electrons, but we can find the charge Q, all right? We can find the charge Q and then convert that to electrons. So the formula is going to have W, V, and Q, and then we'll convert Q to the number of electrons. All right, so right away the formula that comes to mind is V equals W over Q. We're trying to find Q, so, right, switch the Q and the V, and we've got a formula that we can use. Q equals W over V. Okay? Now, let's convert the 500 millijoules to joules. All right, millijoules. All right, millijoules to joules. One big giant joule is 1,000 little millijoules. Okay, 500 divided by 1,000 is 0.5. All right, joules. Okay. Okay, so we've got 0.5 joules, all right, and we want to change 20,000 microvolts to volts. Okay, 20,000 microvolts, okay, microvolts to volts. Get rid of the microvolts, top and bottom. Okay, that's why I put the microvolts down here, so they go away. 1 volt is 1 million, all right, microvolts. 20,000 divided by, we could just move the decimal place 6, right? So instead of here, all right, we've got 20,000 divided by 1 million. Okay, 0.02, move this 6 places. 1, 2, 3, 4, 5, 6, right? So it's 0.02 volts. All right, so that's microvolts to volts. All right, 0.020 volts. Okay, so here we go. Let's put the equation back that we figured out before. All right, Q is equal to W over V. Okay, now, W, 0.5 joules. 0.5 joules. V, 0.02. 0.02 volts. Okay, 0.5 divided by 0.02 is 25. So the charge is 25 coulombs. Right, now, I want to know how many electrons that is. how many electrons? Okay, so, all right, 25 coulombs. All right, there's two ways you could do this. Okay, 25 coulombs. All right, we can either say that 1 coulomb is this many electrons. Okay, or we can say 1 electron, all right, is this many coulombs. Okay, I'm not going to bother with the negatives. Okay, I know that electrons are negative. All right, they're asking for how many. All right, so we want the answer to come out positive anyway. So I'm not going to bother with the fact that coulombs of electrons would be negative. All right, this would be negative, this would be negative, this would be negative, right? All those negatives are going to cancel. Okay, so 25 times 6.25 to the 18th, all right, is 1.56, all right, times 10 to the 20th electrons. And down here, we should get the same answer. 25 divided by 1.6 to the negative 19. Ah, good. 1.56 times 10 to the 20th electrons. All right, either way, all right, it's true that 1 coulomb is this many electrons, so that works. It's also true that 1 electron is this many coulombs, so that works. Okay, so in this section, we were talking about voltage. Voltage is the amount of electrical energy. Take a quick little look at the equation. All right. Voltage is the amount of electrical energy per charge, which is usually 1 coulomb. How much energy per coulomb? All right. If each of these little dots represents a coulomb, if you have 6 volts, then this coulomb, all right, which is really 6.25 times 10 to the 18th electrons, this coulomb has 6 joules. 6 joules per each coulomb. All right. Keep in mind that in a series circuit, if you've got, for example, 6 volts, and 2 resistors, then when you add up the voltage that each resistor gets, it's got to add up to the 6 volts coming out of the battery. So the voltages in series resistors do not have to be the same, but they do have to add up to the battery. In a parallel circuit, all the resistors have to have the same voltage as the battery does. All right? I would almost suggest, since it's kind of tricky keeping track of the difference between current and voltage, I would almost suggest to you that you rewatch the beginning of the current section video, 8.2, just the part about the little coulombs, right, going around the series circuit, going around the parallel circuit, how it works, and rewatch the beginning of this video, watching the little coulombs going around the series circuit and around the parallel circuit, how voltage works, right, for series and parallel. So you want to see how current works in series and parallel, and how voltage works in series and parallel, and how current is different from voltage. All right? I'll see you in the next section.